My name is Caleb Harris, and the purpose of the Constant Velocity Lab was to compare the actual uniform motion of an object to a computational model of the object's uniform motion. My real-world model is rolling a lacrosse ball across a dorm floor. The computational model represents ideal uniform motion of the same lacrosse ball. The model follows Newton's first law of motion, which states if there is no net force, then the velocity will remain constant. This is shown by the kinematic equation Vf is equal to V naught plus acceleration times time. Vf is the final velocity in meters per second, while V naught is the initial velocity also in meters per second. A represents acceleration in meters per second squared, and T represents time in seconds. In this scenario, the acceleration is 0, proving that the velocity is constant throughout the object's motion. The main result of the lab was discrepancy between the computational model and the object's actual motion. As seen in my graph, the computational model increases its position to the right, which represents the positive x direction. However, the experimental motion of the object stops increasing in the positive x direction around 1 meter. This observation is due to Newton's second law of motion, which is represented by the equation F is equal to mass times acceleration. F is force in newtons, and m is mass in kilograms. After copying the starter code, the only thing that I had to edit was the system's mass, initial conditions, and the time of the while loop, as you can see here. I said it earlier, the net force is 0 in the computational model, so that is why I left the F net vector as 0, 0, 0. This allows uniform motion. Running the program, you can see the ball increasing in the positive x direction with a positive constant velocity. In my video, the lacrosse ball moves in the positive x direction, but is experiencing a net force acting against its velocity, which results in an acceleration in the negative x direction. The system is a lacrosse ball, and the surroundings are everything else in the universe. The initial velocity is 0.9908 meters per second in the x dimension and 0 in the y and z dimensions. The initial position of the ball is negative 0.00399 meters in the x dimension and 0 in the y and z dimensions. The computational model was used because it represents true uniform motion. There is no net force in the simulation, so the ball's velocity is the same for all time values. This differs from the experimental data because the ball experiences a net force. In the y dimension, the net force is 0 because the gravitational and normal forces cancel out. However, the kinetic friction force acts in the negative x direction, which opposes the ball's velocity, resulting in negative acceleration. This observation relates to Newton's second law of motion, which states when a net force acts on an object, the object will accelerate in the direction of the net force. This is shown in the line graph, where experimental position stops at around 1.25 meters. If I flip the axis, the ball would move in the negative x dimension with a negative velocity. Additionally, the ball would start with a positive position of 0.003099 meters. Switching the axis will not affect the y and z dimensions. It is possible to say how many forces are added to get no net force. By going through each dimension, we can identify whether the forces cancel out or there is a net force, resulting in acceleration. Possible sources of error might be inaccurately placing the axis or incorrectly placing the calibration stick. As you can see in my video, the x-axis does not stay in the middle of the ball.